In the first section of this video, we're going to take a visual look at how we might do arithmetic with points in the plane, so that we can see why the formulae for complex numbers are appropriate. First, recall how we describe the position of a point in the plane. The easiest way is to use two axes, the x-axis and the y-axis, and measure the distances x and y from the point to these axes. The pair xy are then called the Cartesian coordinates of the point, after René Descartes, the 17th century French philosopher and mathematician. But there's another way to describe a point's position in relation to these axes, at least for points other than the origin. This time, we measure the distance r from the point to the origin, and the angle theta in radians round from the positive x-axis in an anti-clockwise manner. We've written this pair of numbers, r theta, with angle brackets. They're called polar coordinates. Notice that the distance r is always positive. But the angle theta can be positive or negative. A clockwise angle gives a negative value for theta. Also notice that for a given point, the angle theta isn't unique. You can add or subtract 2 pi or any integer multiple of 2 pi to theta. That can be a bit of a problem, as you'll see later. So how can we do arithmetic with points? Addition is easy. It's just vector addition. Given any 2 points, x1, y1, and x2, y2, their sum is x1 plus x2, y1 plus y2. Notice that the 2 points, their sum, and the origin form a parallelogram. It can be helpful to think of this in terms of translations. Each point xy corresponds to a translation of the plane, the one which takes 0, 0 to xy. If we perform two translations, first the one corresponding to x1, y1, and then the one corresponding to x2, y2, the net effect is to perform the translation corresponding to x1 plus x2, y1 plus y2. It's not so obvious how to multiply points, but we can get a clue by examining the rules for multiplying positive and negative real numbers. Here they are in a table. It's the last entry which some people find puzzling. Why should -1 times -1 equal +1? If we think of 1 and -1 as points 1, 0 and -1, 0 on the x-axis, then the table can be written in polar coordinates as follows. And this helps, so long as you remember that the second coordinate, the angle, isn't unique. The last entry could be rewritten as 1, 2 pi. And now a pattern has emerged. It looks as if we get the second coordinate by adding. Pi plus pi gives 2 pi. The first coordinates are all 1, of course, but a reasonable guess is that they have to be multiplied. So this suggests the following rule. Given any 2 points, r1, theta 1, and r2, theta 2, then their product is r1 times r2, theta 1 plus theta 2. In other words, multiply the r's and add the thetas. Like the sum, the product has a useful geometric interpretation. Each point, r theta corresponds to a scaling by r and a rotation by theta. If we perform two such operations, the first corresponding to r1 theta 1 and the second corresponding to r2 theta 2, the net effect corresponds to r1 times r2, theta 1 plus theta 2. With this geometric interpretation, the rule that -1 times -1 equals +1 makes perfect sense. The point -10 corresponds to a half turn about the origin, so -1 times -1 corresponds to a full turn about the origin, and that brings every point back where it started. Now let's try using the rule to multiply the point 0, 1 by itself. In polar coordinates, we get 1 pi by 2 times 1 pi by 2 equal to 1 pi, which is the polar expression for the point -1, 0. That is, 2 quarter turns make a half turn. Thus, 0, 1 acts as a square root of -1, and we call it I, which stands for imaginary. With the help of I, we can represent points in the plane as follows. xy equals x times 1, 0 plus y times 0, 1, which we can write as x plus yi, or, equivalently, x plus iy. In this form, the point is called a complex number. It's usually denoted by the letter z, and we call x and y its real and imaginary parts. The polar coordinates r theta have special names when we treat z equals x plus iy as a complex number. We call r the modulus of z, written z with lines either side of it, and we call theta an argument of z, written arg z. So any complex number can be written either in terms of its Cartesian coordinates xy, that's its Cartesian form, or in terms of its polar coordinates r theta, that's its polar form. Apart, that is, from 0, which doesn't have a polar form. Always remember that a complex number z doesn't have a unique argument. We try to avoid this problem by taking arg z, with a capital A, to be the argument of z which lies between -pi and +pi. This is called the principal argument of z, and it's the one we normally use. Unfortunately, as z crosses the negative real axis, the principal argument jumps by 2 pi, and that can sometimes cause problems. If we want to divide complex numbers rather than multiply them, we can use a similar technique. Remember that for multiplication, the modulus of the product is the product of the moduli, and an argument of the product can be found by adding arguments. Well, for division, we just change the product to a quotient and change the sum of arguments to a difference. Let's look at an important special case when the numerator, z1, is 1. That is, we're just taking the reciprocal of a complex number. Here the modulus of 1 over z is 1 over the modulus of z. This means there's a close connection between reciprocals and the unit circle, with centre 0 and radius 1. If z is outside the unit circle, then 1 over z is inside it, and vice versa. Furthermore, an argument of 1 over z is minus an argument of z. So if z is in the upper half plane, then 1 over z is in the lower half plane, and vice versa. Now watch how 1 over z behaves as z varies. Notice that when z goes far from 0, 1 over z goes close to 0, and vice versa. We can now apply these geometric ideas to a complex number z lying on the unit circle. Since the modulus of the number is 1, it can be written in the polar form z equals cos theta plus I sine theta. Using our geometric interpretation, it's then easy to construct the powers z squared, z cubed, and so on. They all have modulus 1, and their arguments are 2 theta, 3 theta, etc. So the polar forms of the powers are z squared equals cos 2 theta plus I sine 2 theta, and, more generally, z to the power of n equals cos n theta plus I sine n theta. This formula also holds for negative powers, and it's called de Moivre's theorem. De Moivre's theorem is very useful for calculating the roots of complex numbers. For example, suppose we wanted to find all the solutions of the equation z to the power of 6 equals 1. The solutions all lie on the unit circle. For example, z equals 1 is a solution. Other solutions are of the form cos 6 theta plus I sine 6 theta, where 6 theta is either 2 pi or any multiple of 2 pi. Thus we could take theta equal to 2 pi by 6, or theta equal to 4 pi by 6, and so on. So there are 6 complex numbers z such that z to the power of 6 equals 1. And for the same reason there are n complex numbers z such that z to the power of n equals 1. They're called the nth roots of unity, and they form a regular n-sided polygon. A similar approach can be used to solve any equation z to the power of n equals w, for any complex number w, whether or not it lies on the unit circle. For example, suppose we want to solve z to the power of 7 equals w, where w is this point here. We choose the modulus of z to be the modulus of w to the power of 1/7, and take arg z to satisfy arg z equals 1/7 times arg w. That is, we choose arg z so that 7 times it is an argument of w. Once again, we get 7 different 7th roots for a non-zero w. Watch how each of these values of z satisfies z to the power of 7 equals w. We can also see from this picture how the set of 7th roots varies as w varies. When w is outside the unit circle, then the roots are outside as well. When w is inside the circle, then the roots are also inside.